Our topic for today is going to be estimating frequency moments. So let's set up the problem. We have a universe, U, and that ranges, takes values, let's say without loss of generality, 1, 2, and so on. And we are receiving a stream of data items, and each data item is drawn from this universe. And so the first item shows up, that's x1. Second item shows up, x2. Third item shows up, x3, and so on up to xm. And there can be repetitions within these items that show up in the data stream. So one way to think of this would be, for example, data packets that go through a node of the network. And these XIs could indicate the IP addresses, the source destination pairs of each IP address. And this might be able to give you some information about the flow of information or data packets within the network. And that's just one example. There are a variety of ways in which we can interpret this stream of data. And we're just interested in understanding the stream of data. In particular, we are interested in understanding what is broadly called the kth frequency moments. So let's pick an item j in the universe. Fj denotes the number of occurrences of the item j in the stream, throughout the stream, from all the way from x1 through xm. Anytime j occurs, fj is incremented. Let's think of it that way. Now, the kth frequency moment is defined as fk, was denoted fk, and it's defined as the summation over all items in the universe. Let's use the notation j to represent the items in the universe. Summation over j, fj raised to the power k. As it turns out, this notion of kth frequency moment captures a large number of nice characteristics. And now notice that k is a parameter, and as the parameter varies, we get various insights about the data stream. So let's try to get a sense for what these kth moments capture. We're not going to be completely thorough in our treatment. We're going to provide a broad brush stroke, if you will, of the landscape of problems and ideas. So what happens as k tends to infinity? Notice that the kth frequency moment, when k tends to infinity, will be dominated by the most frequent term, because the fj corresponding to the most frequent term, say j, will be raised to the power infinity, and that's going to be larger than, that quantity is going to be larger than the other frequencies raised to the infinity. Well, we're talking about k as it goes towards infinity. And so based on this intuition, what are we going to do? We're just going to conveniently redefine f infinity, um, the infinity frequency norm, the infinity frequency moment, as just uh, the frequency of the most frequent item. Let's look at the other extreme. What happens when k equals 0? Now this begs the question, what is 0 raised to the 0? Because what happens if if there is a positive frequency, well, that will be raised to the power 0, and we know that that value is 1. But if it's 0 raised to the 0, well, we're just going to, by convention, use the value 0 for 0 raised to the 0. Okay? this is quite nice because now F0, the 0th frequency moment, counts the number of distinct elements, because any element that has a non-zero frequency, that item Fj will be raised to the power 0 and will count as 1. And all items that have 0 frequency, on the other hand, will not be counted. So F0 will just count the number of distinct elements. So you see that F infinity has a nice interpretation. F0 also has a nice interpretation. Let's look at k equals 1. And this simply counts the stream length, the number of items that appeared in the number of times various items appeared in the stream. Because every time, so think about this. Each item, if it appears fj times, it will account fj towards the summation. And so when you sum over all the items, these fj's will add up to the length of the stream. Now we're going to talk about k equal to 2, which is very interesting, and it's perhaps the most interesting and important frequency moment. So just to be clear, we're talking about F2, which is the summation over all items in the universe J, Fj squared. If you think about it, this Fj squared intuitively measures how much the Fj's vary. And so in fact, if we want to compute the variance of these Fj values, then this second, I mean the second frequency moment is useful. But that's not all. There are some other surprising ways in which this will be useful. For example, in the in databases, if you have a table that you join with itself, this is a self join, and let's say you join the table with itself based on a particular attribute. Okay, the frequency of values that the attribute takes, let's say, represents fj's. Then the size of the self join is going to be given by this second frequency moment. So think about why that would be the case. So here we again see one more application. So as you can imagine, F2 shows up in a variety of contexts. And so it's just a very interesting and important quantity to compute. And as it turns out, the first paper that talked about these frequency moments in the context of streaming sort of became a very seminal paper, one that kind of opened up the floodgates for a number of different papers that appeared in this area. So this is a paper by Alan, Nogalan, Matthias, and Szegedy. Appeared, I believe, in Stock 96 and later as a journal version in JCSS 99. The title being The Space Complexity of Approximating the Frequency Moments. So this is a big deal because this paper ended up getting the Gödel Prize for 2005. This is a prize given to the authors of papers that end up having a lot of influence over a period of time. So another example of a Gödel Prize winning paper is the Primes in P paper by Professor Manindra Agarwal and his students. So you can imagine that this prize is given to papers that have had significant impact both at the time that they were published as well as over a period of time, because they usually are papers that um, have a lot of impact over a period of time. And in this case, the whole field of streaming algorithms was opened up and studied in depth, uh, in large part because of the beauty of this paper and the beauty of the algorithm that they have presented. So in fact, that's one of the algorithms that they presented is what we're going to talk about today. In particular, we're going to home right into the most interesting frequency moment, the second frequency moment. So yeah, without further ado, let's get to the second frequency moment. Let's begin by an estimator, a basic estimator. This will not be the final estimator that we arrive at, but it'll just help us get a sense for what's going on. And just to remind ourselves, we are estimating F2, which is the second frequency moment. So here's how the algorithm goes. Now, H is a hash function that takes elements from the universe and maps it to either -1 or +1. And such random variables um, that either take the value -1 or +1 are often called Rademacher variables. But that's an aside. So we're going to assume that this H is drawn uniformly at random from a strongly four-wise independent family of hash functions. Okay, so now having drawn that hash function, we initialize a counter z equal to 0, and now let the stream start. Okay, now the elements stream one by one, and for each element, so the elements go from x1 to x2 to x3 and so on. Let's say we have element xi at our hand right now. What do we do with that? We hash that element using h. So we get h of xi. And then we simply increment z with h of xi. Now keep in mind, h of xi can be either positive or negative. And so some of the elements are going to increment it, some of the elements are going to decrement it. But keep in mind, if there's an element that increments it, in other words, h of xi is +1, then h of xi will continue to be +1 throughout the execution of this algorithm. And vice versa, if h of xi ends up being negative, then it's going to be negative throughout. Okay, so now we let the stream run through, and we update z as and when a new item comes in. And at the end, we simply return z squared as the required estimate of F2. So this is pretty amazing, because at first sight, it's not clear at all as to why this algorithm works. The only intuition that I can get, at least, is the following, that z starts off at 0, and then some elements randomly, uniformly at random, pull z on the positive direction, and other items pull z on the negative direction. So there is this sort of a tug of war, and in this tug of war, if the frequency of items is about the same for all items, then the tug of war is going to be even. Whereas if some items are going to be having higher frequency, then the tug of war is going to move either in the positive direction or in the negative direction. And so remember that F2 is a measure that captures how much the frequencies vary, and this tug of war also does somewhat of the same thing. But apart from that, we really need to analyze it a bit more carefully to really see what's going on. So the first thing we need to do is to convince ourselves that this is in fact an estimator. In fact, we need to ask ourselves: is this even a, an unbiased estimator? And what do we mean by that? Is this z squared that we are claiming is an estimator? What is its expected value? Does that match the expected value of F2? If it does, then it would be an unbiased estimator. It still wouldn't be wouldn't necessarily be a good estimator, because it depends on the variance of z squared and how close it is to F2 on average, and with high probability, and so on and so forth. We haven't we're not even going there yet. What we want for now is to establish that z squared is an unbiased estimator. In other words, the expectation of z squared is actually um, f2. Okay, so let's establish that to begin with. So the expectation of z squared is well, summation. So let's just expand out z squared. That's nothing. Z is the summation over all items in the universe, hj times fj. Okay, that's because each item pulls it either in the positive direction or the negative direction, depending on hj value, for fj number of times. Okay, that quantity, that's z, and the whole squared gives you z squared. Okay, and now let's expand this out. We will get two types of terms. In the first type of terms, we will have hj squared, and in this in if you notice, hj squared, whether hj being +1 or -1, the squared value is going to be a +1. So in this case, the hj's can be essentially hj squared can be replaced by a 1. The other type of other set of terms is those which are of the form that have not hj squared, but hj times hl, where j and l are two different elements in the universe. Okay, and as you can see, when you apply the linearity of expectation, and also apply the fact that hj squared is simply just +1. The first type of terms give you this summation over all items in the universe, fj squared. And remember, this is simply our f2, what we want to estimate. And let's look at the second term. Now, the expectation has been brought in based on due to linearity of expectation, and fj and fl are not random variables, so they can be brought out. hj and hl are, on the other hand, random variables. But here's the interesting thing. We remember we have a strongly four-wise independent hash function here, and so hj and hl are independent of each other. So the expectation of their product can be written as the product of their expectations, but each hj on expectation is 0, because it's +1 with probability half and -1 with probability half. And as a result, the expectation of hj or hl, for that matter, they're all going to be equal to 0, and so this product ends up being a 0, which means that this entire term vanishes. and we're left with just F2. So this is pretty neat. The estimator that we have is an unbiased estimator, but that's obviously not all. What we really want is a good epsilon delta approximation. What do we mean by that? For a particular for these particular epsilon and delta values, we want to ensure that our estimate is within an epsilon fraction of the true value f2 with probability at least 1 minus delta. And for this, we need to be a bit more careful, but this is from now on, these are techniques that we have seen before. So what is our roadmap now? We simply repeat the basic estimator in parallel several times, and we take the average, and this will mean that that we can, by this means we can reduce the variance, and then use Chebyshev's inequality to get the required epsilon delta approximation. So for that, first let's figure out what the variance is of z squared, just the basic estimator, because we need to know how much we need to reduce it. So for that, we need to know how much we already have just in the basic estimator. The variance of z squared has these two terms, and the second term is e of z squared the whole squared. What is e of z squared? Well, we already know what that is. That's just f2. So the second term is really f2 squared. So that one's already done. Our worry now is about e of z to the 4. What is this e of z to the 4? Well, let's expand it out. It's going to be the expectation over the summation over items in the universe. We use J to denote these items, and it's a summation over H, summation over J, H, J, F, J. That's just Z, but then this whole summation raised to the power 4 will be our Z to the 4. And if we have the patience to expand this out, we're going to get a long series of terms. In particular, we're going to get some cardinality of u raised to the power 4 terms. So that's pretty long and boring in some sense, but let's see if there's some pattern that emerges. The terms can have one of two forms. There could be, there's a possibility, some of the terms are going to have one of the indices. So notice that these terms are of the form hj1, hj2, hj3, hj4 times fj1, fj2, fj3, fj4. And these indices j1, j2, j3, and j4 can take on any value from u cross u cross u cross u. Okay. Now, if there is an index value that is appearing, that is different from the other three index values, then we have something nice happening. The entire term simply vanishes. Why? Because when we take the expectation of the product, we can apply the fact that it's a we have a four-wise independent hash function, so it ends up being e of h j1 times e of h j2 times e of h j3 times e of h j4, and let's say j4 without loss of generality is the index that is different from all others. That e of h j4 will end up being 0 because, as we just mentioned a little while ago, the expectation of any one h j4 is going to be 0 because it's either plus 1 with probability half or minus 1 with probability half. So all of those terms in which there's at least one index that's different from all others are going to vanish. So what are we going to be left with? We're going to be left with the cases where the indices are either pairs or quadruples, meaning so either of the form h of j raised to the power 4 or h of j squared times h of l squared. So I'm calling h of j to the power 4 as quads and h of j squared times h of l squared as pairs. But of course we know that h of j squared is going to be plus 1. H of L squared is going to be plus 1. In a similar way, h of j raised to the power 4 is also going to be plus 1. So we can simply write this e of z to the power 4 as summation over j fj to the power 4 plus 6 times summation over all pairs j and l fj squared fl squared. Now where does the 6 come from? We get the 6 from the following reasoning. Now we have 4 indices. Out of these, 2 of them are our j's, the 2 smaller ones, and then 2 of them are l's. Now given a particular j and l, we have 4 choose 2 locations or pairs of locations in which the j values can fall, and that's why we have the 4 choose 2 over there, and as a result we get a 6 coefficient here. But let's recall what f2 is. Okay, so remember that we've reached a certain value, a certain expression for e of z to the 4. In order to proceed, just let's look at what f2 squared is. What is f2 squared? It's just the summation over all j fj squared the whole square. And of course, when we expand that out, we get summation over j fj squared plus twice the summation over all j and l fj squared fl squared. This means that 3 times f2 squared is going to be certainly larger than what we have over here. So we apply that bound to get our required bound on e of z to the 4. So e of z to the 4 is at most 3 times f2 squared. Okay. Now going back to the variance of z squared, we can apply our bound on e of z to the 4, and that's going to be 3 f2 squared. And we already know that e of z squared the whole squared is f2 squared also. So that's going to, this variance of z squared ends up being at most twice f2 squared. Okay, so just reminding ourselves of the roadmap, we now have a handle on the variance of z squared for the basic estimator. What we need to do is figure out how to repeat it in parallel, and remember this this variance is too much. We need to be able to reduce the variance a little bit, and for that we will repeat this basic estimator and repeat it, and therefore reduce the variance to a convenient value, so that we can then apply Chebyshev's inequality in order to get the epsilon delta estimator that we want. Okay, so here's our final algorithm. So we're ready to state the final algorithm, and as you can imagine, this is simply the basic estimator just repeated in parallel several times. In particular, we're repeating it t times. And what is that exact value of t? That's going to be fixed later. And recall these hash functions h1, h2 up to ht are all drawn uniformly at random from a strongly 4 wise independent family. and these hash functions map the universe to either +1 or -1. Um, so now, instead of one counter that we had previously, we had just Z. Now we have Zi's where I ranges from 1 to T. And as each now allow the stream to pass by. As each item in the stream arrives, you look at the item and you hash the item using each of the T hash functions. So for example, when you hash using hi, you get hi of j, you add that to zi, that's the ith counter, and you get the new updated zi. And of course, you do this for all I. And after the stream has gone by, we are left with T counters with various values in them. We simply square each of the ZIs and take the average of those squared values, and that's going to be our estimator. This is our final estimator, and we need to show that this final estimator has all the properties that we need. For example, we already know, for example, that this is an unbiased estimator, but we need to be able to prove that this is an epsilon delta approximation of F2. Okay, it's a matter of figuring out what the appropriate t value is, because once we if we repeat an appropriate number of times, the variance is going to come down sufficiently. So really, that's the only question at hand. Okay, so what's the variance of y? That's just the variance. Remember, y is just z1 squared plus z2 squared and so on up to zt squared divided by t. That's the average of the sum of squares. And so you get the t outside, so you get 1 over t squared times the variance of the summation of squares. Okay, but keep in mind that each one of these z1, z1 squared, z2 squared, they're all essentially the basic estimator, so their variances are the same, and so you can simply think of it as t times the variance of z squared. So there'll be a t in the numerator and t squared in the denominator, so we end up with 1 over t variance of z squared. And we already know that variance of z squared is at most twice f2 squared. So variance of y is at most twice f2 squared divided by t. So what you can see is as you increase t, the variance of y keeps decreasing. So that's useful for us. Now we're now ready to apply Chebyshev's inequality. So let's apply Chebyshev's inequality. What is the probability that y minus the expectation of y is greater than an epsilon fraction of f2? Remember, expectation of y is just f2. So really what we are asking is what is the probability that y deviates from f2 by more than epsilon times f2? And a direct application of Chebyshev's inequality is going to say that it's at most variance of y divided by epsilon f2, and applying the fact that variance of y is at most 2f2 squared by t, we get this expression over here. And we have some cancellations. The f2 squared terms cancel out. We're left with 2 over t epsilon squared. And we want that 2 over t epsilon squared to be delta. That's the probability of the bad event where the random variable, the y value exceeds its epsilon approximation range. And so that has to be at most a delta, which means that we will get that requirement satisfied if we set t to be at least 2 over epsilon squared delta, which is all that we really need. So really, with that, we can conclude that the final algorithm that we stated a little while ago, with t-values set to 2 over epsilon squared delta, is guaranteed to output an estimate y of f2 that ensures that the probability that y deviates from f2 by more than epsilon times f2 is at most a delta. So this is exactly what we wanted, and we have that. So this is a very nice, uh, clean algorithm for what, which is quite surprising, because at first sight, at least, this problem does not come across like as having such a clean algorithm. It's quite surprising, but we do have such an algorithm and a very clean, simple analysis as well. So that brings us to the conclusion of this lecture.